Hi, everybody. We're here in the second half of chapter 4, where we're going to learn about L'Hopital's rule, calculus and curve sketching, and optimization problems. So, yeah, today the goal is to talk about L'Hopital's rule and look at lots of different limits of indeterminate form. Um, then we're going to do curve sketching strategy, which really is stuff that we've all done before, with the second and first derivative test that we've looked at recently. It's just kind of bringing everything together under one roof kind of a thing. And then we'll save Newton's method and the optimization problems for Wednesday, tomorrow. So, um, in case you didn't watch it yesterday, in case you weren't around, we did watch this three blue, one brown video. It's about 6 minutes long because we start off at the 10-minute mark. Um, a good little video about the geometry of L'Hopital's rule. But yeah, either way, here's a little refresher on what we're trying to do with L'Hopital's rule. We're working with limits again, which I'm sure is wonderful to hear. Um, we're looking at the limit as x goes to c of this ratio to functions, f of x and g of x. And the idea is L'Hopital's rule's appropriate when we get to an indeterminate form. So, come on. This says indeterminate form 0 over 0. So the idea is that as x approaches c, f of x goes to 0 and g of x goes to 0. So this fraction looks indeterminate. And indeterminate is different than undefined. Indeterminate means that it really could be anything. Undefined means that it doesn't really exist or something is breaking about math. But really, indeterminate form just means um, we're going to have to dig a little bit deeper to figure out what this actually approaches. It could go all the way to infinity, it could go to negative infinity, or it could be somewhere in between. It could go to a specific limiting value. And the cool thing about L'Hopital's rule is that we are going to be able to utilize the derivative to help us evaluate a limit. So when we're in this case of 0 over 0, um, let's go ahead and look down at this, yeah, this set of things. And let me get this out of the way. Hopefully that's not in the way. Um, what this long string of equations says is that the limit of f of x over g of x ends up being um, the limit of the ratio of the derivatives of f and g, which is kind of surprising. But it's a cool result, and the geometry of it is explained in that video. So one thing I wanted to highlight here is that in this steps to show that these are equivalent, know that we are relying on the fact that f of c is equal to 0 and g of c is equal to 0. So we're getting that indeterminate form thing at the point c. Um, Normally, if you add something on the top of the fraction and the bottom of the fraction, normally that's going to change the value of the fraction. But in this case, both of those are equal to 0, so it doesn't change the overall value of the fraction. So we're able to continue to make a number of tweaks to what we've got and change it from something that looks like the limit of f over g and turn it into the limit of their derivatives. So we're going to be able to look at the ratio of their derivatives and, uh, you know, get a value for this limit that we wouldn't otherwise be able to calculate. All right, so number one, we've got the limit of 5x minus 2x or sine of 2x over x as x goes to 0. And, if we were going to just try to plug it in first, that would give us 5 times 0 minus sine of 0 over 0, which 5 times 0 is 0, sine of 0 is 0, 0 minus 0 is 0. So we are in an indeterminate form, or where we want to be in order to do L'Hopital's rule. So, since we know that's L'Hopital's rule, what I would say is go like this. And normally I write a little L and H above the equal sign here to just let the reader know that I'm utilizing L'Hopital's rule here. But yeah, when we do that, we're going to do the limit as x goes to 0 of, we're taking the derivative of the top and the bottom independently. This isn't the quotient rule. So 5x becomes 5. Negative sine of 2x becomes minus 2 cosine of 2x. That extra 2 there is happening because of the chain rule. And then derivative of x just becomes 1. Okay, cool. So now when we try to plug in 0 in for x, we would get 5 minus 2 cosine of 0. And the cosine of 0 is equal to 1. So this is 5 minus 2, or 3. And we actually get a whole number for this, this limit. And I don't know, real quick, I think it would be good to look at this on a graph. So why don't we open this up? That's a different problem. Let's go 5x minus sine of 2x all over x. And yeah, just to, reinforce what we've got this cool oscillating function. If I go f of 0, it's like, oh no, that's undefined. Because we're not actually getting a value here. That is so interesting. GeoGebra here is like, oh, but the minimum here is 0, 3. So in one part of GeoGebra, we're getting a question mark, and another part of GeoGebra, we're getting 3. I wonder what's happening behind the scenes to make that happen. But what we figured out was by using L'Hopital's rule, we got the value of 3 out as a y value, and that's exactly what we're seeing on the graph. So really, this should be an open circle here. But yeah, that limiting y value is 3. Cool. All right, so here is L'Hopital's rule spelled out as a theorem. These are criteria that we'd want to meet to be able to use L'Hopital's rule. We want both of the functions that we're using to be differentiable at all points in an open interval around the point of interest, C, where we're approaching. And that we want the derivative of g to be non-zero, except possibly at that specific point. And, it might be that point because we need it to be an indeterminate form. But anyways, this opens up the door to a couple new types of indeterminate forms. There's going to be even more that we look at soon. But 0 over 0, classic, good one to use. Also, infinity over infinity, or negative infinity over infinity. Really, any combinations of infinity over infinity are good indeterminate forms that it could go off to infinity, it could go off to negative infinity, it could be some number in between. We don't know, but those forms, those indeterminate forms are good ones to just start using L'Hopital's rule. For the other ones that we will see later, we might need to massage the other forms into forms that look like this so that they're a fraction and we can apply L'Hopital's rule. So for instance, let's scroll down a little bit and find those other forms. This one, if we were going to put in 0 in here, we would get the square root of 0 times the natural log of 0. That would feel like 0 times negative infinity. So, 0 times infinity is another kind of indeterminate form, but we want it to look like 0 over 0 or infinity over infinity, and we will tweak it to get that way. There will also be stuff like 1 to the infinity power, or 0 to the 0 power, or infinity to the 0 power, or infinity minus infinity in this case. All of those are kind of indeterminate forms that you might not know what to do with right away. But if we can change them into a form like 0 over 0 or infinity over infinity, then we're going to be able to utilize L'Hopital's rule and hopefully find the limit. All right, so yeah, there's L'Hopital's rule, not the quotient rule. We're good to keep going. Example number 3. Here we've got this limit as x approaches 0. Um, let's make sure that we try stuff out. So yeah, if we try, oh geez, if we try that point, x equals 0, we would get a to the 0 power minus 1 over 0. And since a to the 0 is equal to 1, we got 1 minus 1 over 0, or 0 over 0. So we are in a good indeterminate form. And the idea would be that we could utilize L'Hopital's rule right off the bat. So we're going to write limit as x goes to 0, and we're going to take the derivative of the top. Here's an exponential function where a is some constant. So we're able to use it's really the chain rule behind the scenes, but this is one that maybe you just have memorized. The natural log of a comes out, and that's times a to the x. When we take the derivative of minus 1, it's just going to go to 0. So that's totally cool. The bottom will be a 1. And then if I plug in x into this one, the natural log of a is still going to be hanging around. And a to the x becomes a to the 0. And so we just get ln of a as an answer. And so the idea here is, yeah, this limiting value is whatever the natural log of a is. In example 3, this is what we got to look at. Here, if I do f of 0, okay, we're getting an undefined point. I wonder, ooh, GeoGebra is mysterious. When I clicked it this time, it gives me an open circle, and it says removable discontinuity. I knew that GeoGebra could do this. It is just not consistent at all when it does. That's super cool. Anyways, so on this one, it is giving us kind of a limiting value there based on the natural log of a. But yeah, if I fill in this discontinuity with the point 0 natural log of a, notice that it fits right in. And no matter, what I change a to, as long as a is a positive number, we don't want to be throwing in negative numbers into the natural log function. Yeah. Notice that things get real crazy if I let anything go down to if I let a go all the way to 0, is bad. We don't want to put 0 into the natural log function either. But yeah, if we're putting in 1/10 into this natural log function, everything's fine. And this point that we found is stitching in that removable discontinuity really nicely. So that's good. Well, let's keep going. Example number 4. Here we've got 2 things where hopefully each one of these gives us a little bit of a new and interesting way to think about this process. So part A, we've got e to the x on top and then this quadratic polynomial on bottom. And you might just want to pause and think about the functions e to the x versus that quadratic function. And in the long run, because we're doing a limit as x goes to infinity, in the long run, is the numerator going to grow faster or the denominator going to grow faster? The numerator is definitely going to grow faster because that is an exponential function and e is definitely bigger than 1. Um, this is going to grow much faster over time. And so we can use L'Hopital's rule on this, and we're going to end up using L'Hopital's rule twice, I think. Um, but the main idea is that this should work with our general gut intuition about what should happen with this fraction. E to the x is going to win the struggle. Even though that this turns out as infinity over infinity from the get-go, if we try plugging in infinity, the e to the x is growing much faster than the quadratic function over time. So we've got an indeterminate form. Let's go ahead and use L'Hopital's rule. Oh, I normally put that over the equal sign. There we go. So the limit as x goes to infinity, let's take the derivative on top, e to the x, derivative on bottom, 10x minus 3. Great. For this one, if we put in infinity in for x, we still get infinity over infinity. And so then again, we're going to use L'Hopital's rule. It is totally fine to use L'Hopital's rule twice in a row. We've got e to the x on top and then 10 on bottom. And notice now we've got infinity over 10, which is, infinity. So this limit diverges that whole, fraction. And it diverges to positive infinity. So that one's good. That one's good to think about L'Hopital's rule as a struggle between numerator and denominator kind of a thing. All right. For part B, we've got this new thing. Let's use purple. Here, if we plug in 0, just to make sure, we'd have 1 minus 1 on top, which is 0. We would have 0 plus 0 on bottom, which is also 0. So we do have an indeterminate form. We could use L'Hopital's rule. L'Hopital's equals, okay. When we take the derivative of negative cosine, we're going to get a positive sign on top. Oh, I forgot to put limit. Limit as x goes to 0 of sine on top, and then 6x plus 7 on bottom. And if we plug in 0 everywhere we see x, we would get 0 over 7. And so the answer is 0. So this is, completely fine. You're able to go to a 0 y value. What I want to caution you against, and this is, coming from the book, is if you were to accidentally just get into a roll, maybe the last problem that you did L'Hopital's rule twice, and you're like, it felt good to get that 10x out of there and turn it into a 10. Maybe I should do that on this problem too. If you did L'Hopital's rule one more time on this, notice that you would get something different. So, this is the way that we worked it out, and we got 0 over 7 equals 0. But if you tried to apply L'Hopital's rule to this part, you would get cosine over 6, which when you plug in 0, cosine of 0 becomes 1, and you would get the answer of 1/6, which is incorrect. So does this mean L'Hopital's rule is not reliable? Well, no, this is going to be fine. We just can't do L'Hopital's rule more times than we need to. And in this case, we're trying to apply L'Hopital's rule in a scenario where it doesn't apply. We are not in an indeterminate form when we get to this answer of 0. It's not 0 over 0, it's 0 over 7. So we stop there. Yeah, but you can get a different answer if you accidentally do L'Hopital's rule when you're not supposed to. Okay. Um, Now we're back to example 5. Here's where we can take something that looks like if we put in 0, this part would go to 0, and this part would go to negative infinity. So right now, this looks like 0 times negative infinity. And that's not a 0 over 0 or infinity over infinity. So we can massage this into L'Hopital's rule um, by changing its form. All right, so let's use blue. Um, this one's not L'Hopital's rule yet. I'm just going to change it so that one of these goes on the bottom of a fraction. And the idea is we could put either of them on the bottom of the fraction, but the one that's going to be easier to work with, even if it's in the denominator, is the square root. So ln of x staying up on top makes a lot of sense because 1 over the ln of x is kind of gross, but 1 over the square root of x isn't that bad. That's just x to the negative 1/2 power, which is doable. 1 over ln of x would be grosser. So I'm going to phrase it this way. And then if we do L'Hopital's rule, we could take the derivative of the top and the bottom. Derivative of natural log is 1 over x. Yeah, here, let's just 1 over the square root of x is x to the negative 1/2. And as we're taking the derivative of x to the negative 1/2, that is negative 1/2 times x to the negative 3/2 when we write it that way. So we can bring that over here and say, yeah, I don't know, negative 1/2 times x to the negative 3/2. I'll just leave it like that. No, I won't. Actually, it'd be good to have, well, 1 over x there. We can do that in the next part. Okay, so this is good. I guess, I guess I didn't verify earlier. Let me make sure that we go back. If I put in, 0 in for x up here, this one would go to negative infinity. And if we put in 0 in for x here, coming from the right, this would go to infinity on bottom because it would look like, 1 over the square root of 0. So we were in an indeterminate form previously. If we think about, are we in an indeterminate form now? Yes, this looks like infinity over, well, 0 to the negative 3/2 power. It's kind of weird to think about. I mean, x to the negative 3/2, yeah, that would be its own thing. Yeah, I think the bottom now is negative infinity. The main thing, though, is that we can continue work with this, and I think that we can find a common factor of 1 over x on top and bottom to simplify this a bit. So let me go ahead and try to make that work. All right, so we've got 1 over x on top. I'm going to pull that negative 1/2 out to the very beginning so that I don't have to worry about it. When I pull a negative 1/2 out of the denominator, it's going to be a negative 2 in the numerator. So I'm just going to throw that out front so that we don't have to worry about it. X to the negative 3/2 power is 1 over x to the 3/2. That's probably a good way to write it so that in the next step, we can subtract exponents. We've got x to the negative 1 over x to the negative 3/2. And so, gosh, what's the best way to do this? Probably, let's go numerator times reciprocal of denominator. I like that the best. We're rewriting that division as a multiplication problem. Let's bring it up here. Oh my goodness. And then negative 2 times the limit of, as x goes to 0 from the right, this is going to be the square root of x. That's left from that. So when we put in 0, we get negative 2 times 0, because the square root of 0 is just 0. And so we get 0 as an answer. And again, that's okay. Yeah, what that tells me in this overall product, the square root of x part of it ends up winning the product war. And that's true. The square root of x does, in fact, grow well, okay, as it goes to 0. I was thinking of going to infinity. Square root of x definitely grows faster than natural log of x. And even, I guess, as we're going to 0, this one takes up the lion's share of the product versus this one. Okay. Cool. Let's do number 6. Here we've got something that ends up looking like, if we try to put in 1, this one looks like 1 over 0. So this first one ends up looking like infinity. The second one ends up looking like 1 over 0, because the natural log of 1 is equal to 0. And so this one ends up being infinity. So it looks like we've got this form where it's infinity minus infinity. And here's where we need to get a little bit of creative. We definitely want to change this into a form so that it looks like one big fraction, so that we can apply L'Hopital's rule. So if we go limit as x goes to 1, let's make a common denominator. So we're just going to multiply those denominators together. I don't think that there's anything fancier to do there. So if we multiply that first fraction by natural log of x over natural log of x, we would get this. And then if we multiply the second fraction by natural log of x, or sorry, not natural log, x minus 1 over x minus 1, there's that second fraction. And then we could combine these together. All right, so we've got x natural log of x, and then minus x plus 1 on top. And then we've got x minus 1 over natural log. Here, actually, I'm going to expand that too. I'm going to go x ln of x minus ln of x on bottom. Okay. And so I think we're in a spot where we can utilize L'Hopital's rule right now. Let's go ahead and, confirm that we are in an indeterminate form. If we put in 1 everywhere, we would get 1 times 0, natural log of 1 is 0, minus 1 plus 1. So this is 0 minus 1 plus 1. So that does go to 0. On the bottom, we've got 1 times 0 minus just a 0. So that's a 0. We are in an indeterminate form. That's great. So since we're in an indeterminate form, we can use L'Hopital's rule and take the derivative of the top and the bottom independently. Oh, I need to write limit. Limit as x goes to 1. Okay. So derivative of the top is, gosh, a product rule between x and ln of x. So let's take the derivative of x first. That would leave us with natural log of x. The other half of the product rule will be leave x alone and then multiply by the derivative of the natural log, which is 1 over x. Okay. So this part is the product rule of x ln of x. And then we continue taking the derivative. So we got to do minus 1 for this minus x, and then the plus 1 just goes to 0. Cool. So that's the derivative of the top. Derivative of the bottom will look similar because we have that natural log. So we're going to get the same x ln of x product rule on bottom. And then minus ln of x should turn into minus 1 over x. Okay. We should be able to continue this. All right. What happens if we put in 1? We get the same thing. It's still 1 minus 1 over 1 minus 1, which is gross. There's gotta be something cool that we can cancel out. Let me see. This might be one where we need to do L'Hopital's rule twice in a row again. All right, so let's clean this up. I'm gonna change color. Let's clean this up on top and bottom. Okay, boom. We've got the natural log of x. X times 1 over x just turns into 1. And so we've got plus 1 minus 1 on top. So that's just going to be natural log of x on top. That's seeming simpler. On bottom, we've got natural log of x plus 1 minus 1 over x. All right. I think if we do L'Hopital's rule on this, we should be good to go. So let's L'Hopital's. We're just taking the derivative of the top. So taking derivative of natural log of x is 1 over x. And then on the bottom, we would have 1 over x. The 1 goes to 0. And then the minus 1 over x would become plus 1 over x squared when we use the power rule on that one. And now we have this common factor of 1 over x everywhere. So I'm going to write this again just so that we're clear. 1 over x on top. And then I'm going to factor out a 1 over x. and get 1 minus 1 over x on bottom, then we can cancel out, well, I guess, yeah, we can cancel out the top and the bottom so that we're just left with limit as x goes to 1 of 1 over 1 minus 1 over x. Okay, now this is maybe a little bit nicer to work with. If we plug in 1, this thing approaches 1 on top and 1 minus 1 on bottom. So it's 1 over 0. Thankfully, this is not an indeterminate form anymore. It really just means that infinity wins. So since, 1 over 0 would be a fraction that continues to get bigger the more that x gets closer to 1 here, yeah, we would write that this is infinity. It diverges. Yeah, that's cool. Let's keep going. Gosh, all right. I know that this is starting to feel like a slog. We've done a number of examples already. Honestly, I'm tempted to do maybe 2 more of these. They shouldn't be too long. And then look over curve sketching, and then we'll be done. So it'll be a little while longer, but I understand too that this is somewhat painful. All right. If we look at this limit and we're thinking about putting in 0 in, this one would have a form that looks something like, well, 1 on the bottom, because 1 plus 0 is just 1. And then 1 over 0 in the exponent part, that would look like infinity. So we've got an indeterminate form. It's 1 to the infinity, which is weird. And in order to make it work, we need to make this look like a fraction. And, notice that it doesn't seem like we're going to be able to do that right away. And so we are going to use a little bit more trickery. So let's say that we've got y is equal to the limit as x goes to 0 from the right of 1 plus x to the 1 over x. Okay, so I'm putting that y in there for a reason, because what I'm about to do is take the natural log of both sides so that we can use logarithm rules to mess with that exponent. But I don't want to lose track of the fact that I've used a log. So if I take the natural log of both sides, we get ln of y is equal to, I could put the natural log on the outside, but remember for continuous functions that the continuous functions and the limits are, interchangeable. So I'm going to write limit as x goes to 0 from the right. Notice that this is okay as a limit to be using with the natural log. We're still in the domain of the natural log. Let's go natural log of 1 plus x to the 1 over x. Okay, and now we're just going to continue playing with that right-hand side for a while. So limit as x goes to 0 from the right. When we've got an exponent inside the natural log, we're allowed to bring that out front. Okay, so that's a property of a natural log. And just to make it clear, we can write this as natural log of 1 plus x on top over x on bottom. And now we're in a nice fraction. If we put in 0 here, the top would go to 0 and the bottom would go to 0. Let's go ahead and do that real quick. Show that off. Nice. So we are in a L'Hopital's rule scenario. Let's change it to a lighter blue. We can use L'Hopital's rule again on this right-hand side. Limit as x goes to 0 from the right. The derivative of that natural log part is going to be 1 over x plus 1, or 1 plus x, sure. The derivative of the bottom is just going to be 1. And so if we simplify this, limit as x goes to 0 from the right of 1 over x plus 1, we plug in 0 and we get the limit 1 over 1. But remember that through this whole string, what we've actually solved is that the natural log of y follows this whole string till we get down here. The natural log of y is what actually equals 1. And so we write that. Oh, geez, that was going to be horrible. Natural log of y equals 1. And then when we raise both sides as exponents on e, we would have y is equal to e to the first power. So, y is equal to e. So our original limit, turns into e. And you might recognize that this is just an alternate form of the limit that we saw converge to e on one of our first activities, maybe in chapter 2. Oh, now I'm interested. Yep. All right. So way back in chapter 2, we looked at the version of this limit where x goes to infinity, and there was a 1 over x here and an x in the top. But notice how this is the same as x going to 0 from the right of, well, where we are, boom, this one. So those have changed places, but we're still approaching e overall. All right, let's keep going. Example number 8. Again, we are in a scenario where we've got a weird exponent going on. In this case, we would be going to 0 to the 0 power if we tried to plug in things right away. We don't want that. We want a fraction to be able to use L'Hopital's rule. So we say y is equal to the limit as x goes to 0 from the right of x to the x power. Then we take the natural log of both sides. Oh, I forgot to write the limit, sorry. Limit x goes to 0 from the right of the natural log of x to the x. Then we're just going to keep messing with the right-hand side. Limit as x goes to 0 from the right of x times the natural log of x. Notice that this is looking very similar to one that we've seen previously with this product. It's looking very similar to that one. And so this isn't a fraction yet, but we can make it a fraction. If we put 1 over x on bottom, that is equivalent to what we just had. And so now the top is going to negative infinity when we put in 0 from the right. The bottom is going to infinity as we put in 0 from the right. And so now we're able to work with L'Hopital's rule. Limit as x goes to 0 from the right. We get a 1 over x on top. We get a minus 1 over x squared on bottom, taking that derivative. And I'm going to go ahead and write that as multiplication so that let's throw -1 on bottom. There we go. That'll settle that. But yeah, limit as x goes to 0 from the right of, well, a negative x. And so this one turns into 0. But remember that is the natural log of y is equal to 0 through this string of equations. So we set up natural log of y is equal to 0. E on both sides makes it y equals e to the 0, which is equal to 1. So our answer for that limit is 1 as a y value. All right, and for the sake of time, I'm going to skip number 9. This is another one where we've got, you know, an exponent, and using a natural log would be a good move again to get to the end. Okay. The next big topic, and this is where we're going to end up, this is not going to be, a whole nother half of the class. It's going to be less than that because we've already done this to some extent. 4.5, though, is focusing in on curve sketching strategy, and it's trying to bring together everything that we've done up to this point under one roof. So domain and symmetry, looking for periodic functions, looking at intercepts and asymptotes. Those are kind of all things that are coming from chapter 1, the very first stuff that we were just talking about functions and making sure that we were up to speed with that. Yeah, steps 1 through 3 are coming from chapter 1. But looking at those things gives us a good base to build off of. In particular, L'Hopital's rule often becomes handy when you're trying to plot asymptotes. Remember that when you're doing asymptotes, you're finding vertical asymptotes when just the denominator of a fraction is equal to 0. You're finding horizontal asymptotes when you're looking at the limit as x goes to infinity or the limit as x goes to negative infinity. And L'Hopital's rule can sometimes be helpful when you're doing those limits. For steps 4 and 5, we're just bringing the stuff in from earlier on in chapter 4, where we're looking for critical points, we're looking for points of inflection, we're doing the first and second derivative tests to look for intervals of increasing and decreasing, and for maxes and mins, so relative extrema. And so for this example, hopefully it doesn't take too long. I'd like to go through those 5 steps and do as best we can. I did a shortened version of those 5 steps here to just make us look for all of these things in a row. Okay. First thing is the domain. For this function, we have a nice polynomial. The domain is just all real numbers. We can put in any number in there. It's completely fine. That might, be more complicated for crazier functions, but for now, this is fine. The intercepts, we'd be looking for x-intercepts and y-intercepts. Probably I don't know. You could decide whichever one's easier if you want to pay attention to it, but without thinking about it too hard, we could just try to look for x-intercepts. These happen when y equals 0. And so we would try to solve this equation. 0 equals 10x cubed minus 6x squared plus x. And we might try to factor this 10x squared minus 6x plus 1. So we're able to pull an x out of there. That means that x equals 0 is going to be a good spot to find an x-intercept. So actually, the point 0, 0 is going to be both an x and a y-intercept. And then for the other part, we would try to factor it further. And after trying to factor it, we would run into some difficulties there. And maybe we would try to use the quadratic formula. For this part, if we try to use the quadratic formula, we've got x equals negative b. So that's a 6, plus or minus the square root of b squared. So that's 36 minus 4ac. So that's 40 all over 2a, which is 20. And the idea here is, once you try to use the quadratic formula, this part called the discriminant, the stuff underneath that square root is going to turn out to be negative. And that means that the other roots of this are actually complex numbers. And so there's only one real root of this cubic function. So we've got one real root. So for now, we've got the point 0, 0 as an x-intercept. If we try the y-intercept, this is when x equals 0. What we would do is try to just plug in 0. So f of 0 equals, 0. When you plug in 0 there, everything just turns into 0. And we get the same stinking point. Sorry. So the origin is both our x and y intercept there. As far as asymptotes, there aren't any. This is just a nice polynomial. Asymptotes would arise if we were working with a rational function. If we wanted to play around with asymptotes, we could look at, probably this one would be a good one. Whenever the denominator of this would equal 0, then we would have a vertical asymptote. Would the denominator of this function ever equal 0? Well, actually, no. Because we've got 2 plus something that's in the range between 1 and negative 1. So actually, that one's not going to have any asymptotes either to speak of. This one's not really either. So honestly, we would need to go and find another example if we're going to play with asymptotes. Honestly, not super critical. Really in calculus, we're here to focus in on the critical points and the intervals and the extrema and that kind of stuff. So let's go ahead and move on to that part. But yeah, asymptotes, none. It's just a polynomial. Let's go to the next part, which is green. All right. Critical points. Okay. For the critical points, we'll take the first derivative of f. We would get 30x squared minus 12x plus 1. And notice that I already wrote this over here. I did the quadratic formula on this so that we could get some values for this pretty quickly. So for our first derivative test, we've got the point 6 minus the square root of 6 over 30. And for this one, we've got 6 plus the square root of 6 over 30. Yeah, and both of those are positive numbers because 6 is greater than the square root of 6. And so if we wanted to find some test points here, the test points I might suggest are, well, we could do a 0 here since everything's positive. We could do 6 over 30 here. So 6 over 30 is 1/5. So I might do 1/5 as a test point because that's directly in between those two roots. And then over here, um, gosh, I'm not sure how big that is, but I guess it's not bigger than 2/5. Uh, let's go ahead and throw a 1 in over here when we do this. So if we look at this, we go f prime of 0. Well, this would be 0, this would be 0, this would be 1. So this is greater than 1. That means that we're increasing on this interval. If I do f prime of 1/5, this would be 30 over 25. This would be 12 over 15, and this would be 1. I believe we're going to be negative. Oh, what am I doing here? These are not ones, these are zeros. Sorry. I believe that when we throw in 1/5 into this, we get a negative number. That means we would be decreasing on this interval. And then if we put in a 1 into this function, we'd have 30 minus 12 plus 1. That's going to be positive. And so, yeah, those critical points help us find, the intervals of increase and decrease. I guess that first interval, I guess I haven't done a good job of writing it in interval notation. We go from negative infinity up to 6 minus the square root of 6 over 30 as an interval of decrease. And then in between those 2 points, 6 minus square root of 6 over 30 to 6 plus square root of 6 over 30. That's an interval of increase. And then the last one, 6 plus square root of 6 over 30 to infinity. That's an interval of decrease. So those are all good things to know. Extrema and, the points of inflection, good grief. Going from this chart, increase to decrease means local max. Decrease to increase means local min. We could verify that with the second derivative. Let's go ahead and do the second derivative real quick. Here we get 60x minus 12. Ooh. So that if we're setting this equal to 0, looking for inflection points, x equals 1/5 is a critical point for the second derivative. And that means that 1/5 is an inflection point. If we went to the left of 1/5, I guess we would make this kind of a chart. 1/5. If we went to the left of 1/5, we would be concave down because the second derivative, let's say at 0, would be negative. And then on the right-hand side, we'd be concave up because the second derivative, let's say evaluated at 1, would be bigger than 0. So yeah, here our test point was 0. Here our test point was 1. But yeah, this is an inflection point. And I think we've identified, most of the important stuff. We could then go on to actually utilize this stuff to sketch the curve. I have completely run out of room. Um, and I think that we've done the important part. Man, I don't know. If we're running out of time in class, feel free to just turn this off. But if you've got a couple minutes and you want to see this, I'm going to go ahead and, we could graph it. It's not going to be anything stupendous. But let's go ahead and just try to sketch this real quick. All right, so we know that we're going through the point 0, 0. I guess let's make this red. We're going through the point 0, 0. Um, we've got an interval of increase leading up to this point, and then decreasing and then increasing. So I might want to make those 2 points real quick. Let's go to, I don't know, let's make it over here and over here. Here's the one where we subtract off the square root of 6. Here's the one where we add on the square root of 6. But yeah, as we go along, um, we would treat this as, what did I do? Oh my goodness. I totally messed up the blue words that I did here. I totally contradicted what I wrote earlier. Sorry. This is increase, this is decrease, and this is increase. For whatever reason, I just decided to, write those backwards. Um, let's go ahead and, yeah, do this. So it's increasing up to this point, then it's decreasing over this interval, and then it's increasing after that. So I might draw some arrows in there just to remind me. Um, but yeah, the concavity changes right in the middle of those two. So we're going to have an inflection point right here. And if I wanted to sketch this, I've anchored it by having an intercept. And I've got these intervals. So I think the best thing that I could do probably is just try to graph it. Um, let's go with this. So, well, and then that's a maximum. We go down here, we have an inflection point. This is a minimum, and then we continue to go up. Um, those concavities work out nicely. So that would be a good sketch. Feel free to, throw that into a graphing calculator and make sure that I'm not too far off base. But yeah, that's a way that you can use everything that we've learned so far to sketch a curve. Thank you for being patient and working through this. Tomorrow we will continue going with stuff, Newton's method, and then we're going to do optimization problems. So if all of this has felt not applied and very theoretical, we're going to work on some cool problems tomorrow. All right, we'll see you then. Bye.